Hey students, welcome to another chemistry class, and today we are going to discuss about another topic, and we're going to talk about isotopes and relative atomic mass. Remember, in our last class we did an introduction to isotopes, and if you can remember, we said isotopes are atoms of the same element with the same atomic number but different mass numbers. So those are isotopes, atoms of the same element which have the same atomic number but they have different mass numbers, or atoms of the same element with the same number of protons but different number of neutrons. That's another way you can put it. So you can say that isotopes are atoms of the same element with the same number of protons but different number of neutrons. An example is hydrogen isotopes. By the way, hydrogen has three isotopes: hydrogen 1, hydrogen 2, and hydrogen 3. In simple terms, we have protium, deuterium, and tritium. Those are the names of the isotopes. Now hydrogen 1 has no neutron, so it is written H11. It has 0 neutrons, and the mass number of protium is 1. And also we have hydrogen 2, which is deuterium, which is written H21, meaning that the mass number is 2 and the atomic number is 1. Remember, the atomic number for isotopes does not change because isotopes have the same number of protons. That one is very important. So for deuterium, which is H21, it has got 1 neutron and 1 proton, therefore the mass number is 2. And hydrogen 3, which is tritium, hydrogen 3, the name is tritium, it is H31. Therefore tritium has got a mass number of 3, and it therefore means it has got 2 neutrons and 1 proton. Therefore that gives you a mass number of 3. I hope that one is understood. So we have so many isotopes. Chlorine also has isotopes, chlorine 35 and chlorine 37. Carbon has also isotopes. We have carbon 12 and carbon 14, and bromine has got isotopes. We have bromine 79 and bromine 81, and so forth and so forth. So isotopes basically are atoms of the same element with the same number of protons but different number of neutrons. They have the same number of protons but different number of neutrons. Don't forget that. It is a common question in exams. Now, having said that, I want to move on and talk about relative atomic mass, which is a very important subtopic in chemistry, and also it is examined most of the time in the exam, so you need to pay attention to this. Now, what do we mean by relative atomic mass? When we are talking about relative atomic mass, or in short RAM, abbreviated as RAM, this is the mass of any atom compared with an atom of carbon 12. It is the average mass of any atom of an element compared with an atom of carbon 12. Now carbon 12 is the reference atom or element that is used for comparison with other elements in the periodic table. So you can simply say that RAM is equal to average mass of one atom of an element divided by half the mass of an atom of carbon 12. So that is basically what RAM is: the mass of an atom of any element compared with an atom of carbon 12. RAM is measured by an instrument which is called a mass spectrometer. So usually in exams you can be given a mass spectrum which you can use for calculation, or you can be given the relative atomic mass or the mass, just the mass of the element. Now, but to accurately determine the relative atomic masses of elements, an instrument that I've mentioned, a mass spectrometer, is used. Now, RAM, or relative atomic mass, has no units. It doesn't have units because it is just a ratio. It is a ratio, like I've said. It is the average mass of one atom of an element divided by a half the mass of an atom of carbon-12. So it is a ratio, therefore has no units. Now I want us to look at a question: how to calculate the relative atomic mass of isotopes. Now I want to say something very important. To calculate the average relative atomic mass of a mixture of isotopes, you need to multiply the percentage abundancy of each of the isotopes by its relative atomic mass, and then add this together to get a whole number, or you can get a whole number or a number containing decimals. It is accepted. I'm going to give you an example of a question, and I'm going to read the question. This question says, naturally occurring bromine is composed of two isotopes, bromine 79 with a percentage abundancy of 50.5% and bromine 81 with a percentage abundance of 49.5%. Calculate the relative atomic mass of naturally occurring bromine. Now that's the question. Now for you to do this, you need to use this formula. RAM is equal to mass times percentage abundancy divided by 100. So that is the formula for finding the relative atomic mass. Mass times percentage abundancy divided by 100. Therefore, we have been given the mass for the two isotopes. We have 79 and 81, and we've been given the percentage abundancy, which is 50.5 and 49.5. So basically the RAM is equal to 79 times 50.5 plus the other isotope 81 times 49.5 divided by 100, and the answer is 79.99. So that answer is correct. You can express the answer in that format, or you can give it as a whole number. 79.99 is equal to 80. So you can give the answer as 80. So that's how you can calculate the relative atomic mass for bromine, and it is very simple. I'll give you another question, and this question reads like this. Chlorine 35 forms 75% of the total mass of chlorine, and chlorine 37 forms 25%. Calculate the RAM of chlorine. So it is very simple. We use the same method that we have used in the above example. RAM is equal to mass times percentage abundancy divided by 100. In this case, we have two isotopes, just like in the first example. So this is going to be, we are given the mass is 35 and the percentage abundance is 75. So that is going to be 35 times 75 plus 37 times 25 divided by 100, and that gives us 35.5. That is the relative atomic mass of chlorine with no units. Now, from these two examples, we have seen that the relative atomic mass of the element is nearer to the mass number of the most abundant isotope. That is the observation that we have made from the two examples, that the RAM is nearer to the mass number of the most abundant isotope, and that is how it is. So now, sometimes in the exam you can be asked to solve for the percentage abundancy and not the relative atomic mass. If you are given the relative atomic mass, but you are not given the percentage abundancy, you can do that calculation very simply going backwards. Now that we know that RAM is equal to mass times percentage abundancy divided by 100, then you can be able to calculate the percentage abundancy if it is not given, but you are given the relative atomic mass. And I'm going to use an example how to calculate the percentage abundancy if you are not given the percentage abundancy, but you happen to be given the relative atomic mass. Now I'm going to give you a question, and this question reads like this. Europium has two isotopes, europium 151 with a mass of 150.916 and europium 153 with a mass of 152.9209. Given that the RAM of europium is 151.96 atomic mass units, calculate the percentage abundancy for each isotope. 3 marks. Now for you to calculate the percentage abundancy, it is very simple. You say RAM is equal to mass times percentage abundancy of the isotopes divided by 100. And it looks like europium has got 2 isotopes, so that is the RAM is equal to mass of isotope 1 times percentage abundancy of isotope 1 plus mass of isotope 2 times percentage abundancy of isotope 2 divided by 100. That gives you RAM. Now if that is the case, 150.916 times X plus 152.9209 times 100 minus X divided by 100. That is the expression. Now I have used X. I have said let the percentage abundancy for europium 151 be X percent. That's why I'm using X. And let the percentage abundancy for europium 153 be, if 151 is X, the other one is 100 minus X. So that's the way to go. So let the percentage abundancy for one isotope be X and the other one is 100 minus X. And when you substitute that in the formula, you find X. You can do that for this example. X is equal to 48%. Therefore, X minus 100 minus X is equal to 52%. The percentage abundancy, therefore, for europium 151 is 48%. And europium 153 is 52%. It's very simple, isn't it? Very good. Now that's how you can calculate RAM, and that is how you can calculate the percentage abundancy for an isotope or for isotopes if you are given such a question. Now we have come to the end of our lesson today. I want to wish you well. Ensure you take more questions on the same subtopic because it is very important and it is examined in KCSE. I have come to the end of the lesson. Ensure that you subscribe to this channel. Ensure you hit the notification bell so that you can be notified of new upcoming videos for the next upcoming lessons. Otherwise, for now, bye bye and see you again.